Hello, you all. This is Darrell Lee Berry Jr. back with some more science and math, physics and astronomy in particular. I'm continuing from yesterday's stream where I was working on the simple harmonic, at least not the simple harmonic oscillator, but the quantum oscillator, even though we talked about the simple harmonic oscillator a bit, to get towards quantum mechanics. So I'll do a brief review of what we did yesterday, not in detail, but just an overview. And then we'll continue because I need to understand this uh, as best as I could by tomorrow. So here's the screen setup today, slightly uh, different than yesterday. So if anybody shows in the chat, I'll go ahead and show the chat so people can see it live as well in the stream. So hopefully people show up. If you do, drop a line. So to recap what we did yesterday, we talked about the simple harmonic oscillator, the classical oscillator, and how it relates to the quantum oscillator and similarities. As long as the amplitude is small, basically all oscillators basically equate to a simple harmonic oscillator. We took the time independent Schrodinger equation in blue and applied the harmonic oscillator potential to it. And from there, we're going to do the analytical power series method of solving uh, for the harmonic oscillator, the quantum harmonic oscillator. We did the substitution of Z for that value that is defined as to simplify the calculation. And then we'll take a look and see how to do the power series to finish simplifying that. And along the way, I did several double derivatives. Uh, so perhaps we can actually fill that out, or maybe not. That'll be a long process. I was looking at this line here. We could actually do the double derivative in that spot, but we know what the derivatives are. So we know that this is the second derivative here of psi, and we know that this is the first derivative of psi. And in essence, we need the second derivative here, no derivative there, and no derivative there, and it should still be of z. And I'll continue with this and see if I can understand this better. The tutoring, by the way, is not on the subjects I'm taking now, on previous subjects. So anybody's interested, I want tutor on quantum 2, and maybe even not quantum 1. Quantum is not my strongest subject. But classical dynamics, pretty good with that. Electrodynamics, I ended up being pretty good with that. It was shaky along the way. Um, Pretty much all the math you need for physics, at least at the basic level. Calculus 2, 3, all that. So let's keep it going. Let's get it started. And I am in Discord if anybody wants to join. Y'all can let me know how the vertical prop looks. It's easier for me to write this way. Continuing with the text, it says shorter equation becomes, now this is where we left off right here with equation 2.79. I want to consider how the Schrodinger equation becomes that. Saying 2.73. Let me rewrite that. So that 2.73. It's saying that becomes this. Actually important. It seems that I put the details in there. This becomes this. Well, if that seems familiar from this equation here, right? So I'm still not seeing exactly the bridge point there. Write this out. I'm going to actually write this 2.73 out. So we have the second derivative of psi with respect to z, which is this, and we confirm the answer with the book answer. That equals z squared minus k. Uh, psi is this. Well, I should go ahead and put that there. We have that. We just plug that in. See what this does. So we see that there's this on both sides. So that cancels. So we're left with this. And let's see what else we can do to, so what we're trying to do is see how it got this. Right? Look at us call this H. They're the same. Then we have d squared h over, is that partial? To the other side, and we can see how this cancels. So it looks like we do end up with what they said, which is d squared h over d z squared minus 2 z dh over d z plus a minus 1 h equals 0. So that is what they have for 2.79 when you plug that in, even though it doesn't seem like it. When you plug that in, that's what we get. I propose to look for solutions to equation 2.79 in the form of power series. So basically what we've done is we've rewritten the wave equation in this form, where now H is the equation. So in this sense, it looks like we have H minus 2, H plus K minus 1, H equals 0. So we have a polynomial-like structured differential equation. So what we can do, so it says now H of z is the function that we're solving for now. What they're saying is we can solve for that as a power series. So we can write H as a series of functions, a naught plus a1 z plus a2 z squared plus a3 z cubed plus what's going to be the sum j equals 0 to infinity of a j and z j. Basically, we're going to go ahead and solve or find an h that satisfies the altered time independent Schrodinger equation in the form of this polynomial-like solution for the polynomial-like equation. Since we have h first derivative and h second derivative, we have to take the derivatives of those. So we write this, h equals take the derivative with respect to J was G. Some of the more complicated differential equations I was talking about yesterday. Seems right. We have that. See that there is a slightly different from mine. Each first derivative is the same, but the H second derivative is quite different. So let's see what I can do to get this the same. And thank you for joining. Who's joined? Remember to drop a line. So see if I can remember this. So 0 and 1 are going to make this 0. So we can say that this is J equals 2 to infinity. J minus 1, a J minus 2. Uh, what we need to do now is get the exponent to be the same. So J equals J minus 2. So this is now starting to look like what we have. So that's going to be integral. Say J equals J plus 2. j equals j plus 2. I literally replace j plus 2 where j was. That means I have the sum of j equals 0 to infinity. Remember, everywhere I see j is j plus 2. So that's j plus 2, j plus 1, a, j plus 2, z, j. And we can do the same thing here with j equals j plus 1. Uh, 0 gives you 0. So j equals j plus 1. So we have the sum j equals 0, j plus 1, a, j plus 1, z, j. We put this into equation 2.8, which I have there. I wonder why they say equation 2.8. I think it would be equation 2.9. Not 2.9, but 2.79. I want to plug this straight into 2.79 and see what I get. So we would have sum j equals 0 to infinity of j plus 2, j plus 1, a, j plus 2, cj minus 2, z plus 1, a, j plus 1, zj. Plus a minus 1, aj, zj, and all equals 0. So we see that each term has one of these. We can cancel that out. And So now we have j plus 2, j plus 1, a j plus 2 minus 2 sig v j plus 1, a j plus 1 plus k minus 1, aj equals 0. This is looking close to what oh, I see what I missed there. I missed a z was still sitting out there. That's why they left that -1 there. Mhm. Distribute that z. So that's one thing about the textbook. They skip a lot of steps. So this actually becomes j equals 0, infinity, j plus 2, j plus 1, a, j plus 2, zj minus 2, j plus 1, a, j plus 1. And this becomes the j plus 1 plus k minus 1, aj, j equals 0. Now I have to get rid of that exponent there. 0 doesn't equal 1, doesn't equal 0. So there must be a way to get rid of it while I'm here. So what I'm going to do is to go back, at least in my case. I'm sure there's a way to do it, but I just don't know it. I'm going to keep that negative there since I have a z on the second term that's going to be multiplied in. So I'm on the right track. So we have the sum to infinity, which I'll put on the outside, j plus 2, j plus 1, a, j plus 2, zj, plus, I'm going to distribute this 2 first derivative now, or 2z times the first derivative, 2z, summation is outside, j, a, j, d, j minus 1, plus k minus 1, then we have aj, dj equals 0, and this distributes. So now we can start to cancel some things after we distribute that. And actually we can do that now. So that's going to cancel. So this is going to be these two together, going to be j and this is going to be J. Now we can say J plus 2, J plus 1, A, J plus 2, plus 2, J, AJ, plus K minus 1, AJ, equals 0. And this looks to be what the book has. So now we're looking at this equation right here. J plus 1, J plus 2, AJ plus 2. So I have a plus, they have a minus, so 2JAJ plus K minus 1AJ equals 0. I think that was a typo, or they're just doing it a different way. You put that into 2.79. I guess that's the same thing. I just wrote it differently. 2.8 is this equation here. It's not, and it must have meant 2.79. It must have been a typo. Why do we have a minus? Is that right? Yeah, I did drop off my negative sign. That's a minus right there. All right, so now we have exactly what the book has, and then we can solve for AJ over J plus 2. So A, J plus 2 equals negative K, or I should say 1 minus K AJ plus 2J AJ over J plus 1, J plus 2. So that equals AJ 1 minus K plus 2J. That's good. J plus 1, J plus 2. A J plus 2. Right? So this is called the recursion formula, which allows us to get the respective values of AJ plus 2 to solve the equation. Right? So this recursion formula, it says, is entirely equivalent to the Schrodinger equation. Starting with A naught, it generates all even number coefficients. And starting with A1, it generates all odd number coefficients. So if I put in A0, give me an even number, even coefficient. Put in 1, give me 3, and so on and so forth. So starting from A2 on up. So H, the complete solution, equals H even plus H odd. Is going to be A0 plus H2 Z squared plus plus to be A1 plus A3 Z Q plus, and that'll be our solutions. All right. Like we finished it just about. That's a good place to stop. Got a nice round point where we got to uh the equivalent solution of H, which is the substitution simpler variable that we input for psi for the harmonic oscillator so that we can solve a simpler differential equation and still get to the same answer because it's equivalent. So I may be back later. And hey, what's going on, Sean? Good to see you. Yeah, I figured I'd come in. Yeah, normally I would probably talk about this on my STEM channel, but I'm learning this still and I just figured it out along the way. So I figured let me come here for a more casual going through it. Uh, but I'll come back. I was up all night, but I still want to make some progress. I was coding earlier, doing some analysis on my research on the Persepi cluster. So I'm gonna take a nap, and then I'll be back and do some gravitation showing. And then this guy is supposed to be on who was uh, talking about name is Nicholas, who is apparently understands physics and stuff more than all the scientists and everything. So I said if somebody seems sincere, I would talk to him a bit, but also said I'll spend less time. So I'll give him a little bit of time to uh, point out any discrepancies, and that should be entertaining, I guess. So awesome, Sean. Good seeing you. I shall be back in about 6 hours, and I should be back in about 6 hours for a few hours. So I hope I see you then. All right, y'all. Have a good one.